What is meant by a homogeneous expansion is raising the question of what does the homogeneous distribution look like. In order to have homogeneity, you need to have equipartition, and whether that equipartition is done by distance, velocity, rapidity, momentum, kinetic energy, is a relevant question to ask. The dogma that I'm referring to is the assumption that this homogeneity is by distance, and that they have to claim that space stretches in order to get everything to work out, when they could be using homogeneity by a equipartition of rapidity. His next comment is that he takes issue with the idea that there is anything you would not be able to see. And so far, I believe what he's referring to is this demonstration here. But the point I want to make here, I'm not sure if this was the misunderstanding, but there is nothing in here that you shouldn't be able to see. This part of the animation should look the same as basically what was going on back here. You can see there's also an edge over here, but this is not a real edge. It's because of the choice I made of which dots to simulate. Now, ideally, I wouldn't create a distribution randomly between -3 and 3, or rapidities between -3 and 3, but I would choose rapidities between -infinity and +infinity. Here's a page from Ned Wright's Frequently Asked Questions in Cosmology. And let's come down here to why haven't the cosmic microwave background radiation photons outrun the galaxies in the Big Bang? We come to this article saying the Big Bang was not an explosion from a single point with a center and an edge. Each dot represents a, quote, galaxy, which is not necessarily a true galaxy, but some kind of galaxy-like structure or concentration of mass. Now in this diagram, two of the galaxies have a ring of red photons moving out from them. And this is the key statement, one of the key statements that I would argue with. Most of the photons are cosmic microwave background photons that were present since the Big Bang, but which have been traveling since only 0.0003 billion years after the Big Bang. In particular, these 4 words, present since the Big Bang, 5 words. Now he's kind enough to present a animation of this right here. You can see things expanding right here. But first, the Big Bang happens right here, and then the photons first reach each other, and then the photon first reaches the nearest dot right there. So what's interesting is that this photon was sent during the Big Bang, but it doesn't reach our galaxy until now, because you can see that the dots are spreading apart. That's what they essentially say is the space stretching out between the dots, and that's the phenomenon that creates the redshift, the cosmological redshift. I believe these diagrams do more or less represent the standard model, and there is a boundary. It all might be seen eventually, but as far as that's concerned, this particle and, say, this particle are not yet causally connected. There has not been enough time in the universe for light to pass between this particle and this particle. if they are seeing objects that are 47 billion light years away, that has to be an outlier of Hubble's constant. Recall that Hubble's constant relates how far something is away to its velocity, and so let me run through an argument behind the standard model. We have proposition A, that distance actually means something, and we have Hubble's law, which tells us that velocity is equal to Hubble's constant times the distance. Then we have this observation of objects 47 billion light years away. According to Hubble's law, that implies that there are objects moving faster than light. So what do they go back and do? Well, they decide that proposition A is incorrect. We're absolutely not going to call into question Hubble's law. Instead, we're going to decide that distance is some kind of ephemeral concept. Well, my main point is, if an object is 47 billion light years away right now, then it does not meet Hubble's law, period. Or if the universe is 14 billion years old and objects are 47 billion light years away, it does not meet Hubble's law. There is a different Hubble's constant at different distances. Now, I think it might seem kind of insulting to say that stretchy space is dogma. No one's ever claimed that I'm going to go to hell for believing that space is not stretchy. But I think I have been called anti-scientific or anti-science because I don't think that space stretches. I have been accused of being some kind of religious fanatic because I don't think that space stretches. But what I've never been given is a convincing argument that space stretches. But to be fair, this dogma comes from a fairly well-reasoned question of how we can get homogeneity and isotropy in a expanding universe. In particular, what is so special about equipartition by distance? And so behind this dogma that we have stretchy space is this kind of unanalyzed assumption that homogeneity is equal to equipartition by distance. If we just clear that out and say homogeneity means equipartition by rapidity, then we no longer have a situation where we need to claim this idea of stretchy space. Now, in conclusion, I'd like to try to make this as parallel as I can. The scientific method doesn't mean insisting that you're right and the other party is wrong, but I think what it does mean is entertaining alternative hypotheses. And that means distinguishing them and striving for clarity and trying not to misrepresent the opposing argument, but try to be fair, clearly represent what it's about. This is probably the biggest problem that I have with the standard model is a lack of clarity. So there's nothing I can really point to and say, well, that's wrong, because a lot of the statements made about it are open to interpretation. And I think that a hypothesis that is open to interpretation is not really scientific. That would be called a prophecy if after whatever happens, you can always go back and interpret the data to say, look, we were right. That's called a prophecy. So I think these two things should be treated as alternative hypotheses, the Milne model and the Standard model. And they differ in fundamentally two ways. First, the Milne model uses the Cartesian coordinate system, while the Standard model uses stretchy space. And the Milne model uses equipartition by rapidity, and the Standard model uses equipartition by distance. So in fairness, you may find me arguing dogmatically for the Cartesian coordinate system, and arguing dogmatically for equipartition by rapidity. But what I would really like to see is, a genuine comparison between these two models, with the data. What I've seen is a lot of comparison of the Standard model with the data and saying, how can we make the Standard model fit this data? But what I've never seen is take the data and compare it with the Milne model, and how do we make the Milne model fit with this data? It's never been given the same kind of emphasis. Now, this is the same kind of comparison that Galileo did when he compared Ptolemy's geocentric model for the solar system versus Copernicus's heliocentric model for the solar system. They had some assumptions about the nature of the reality, and eventually they made comparisons to the data, and the heliocentric model won out. Now, my prediction, if the Milne model and Standard model were given the same treatment, the Milne model would win out. Now, am I correct? I don't know. I really don't have enough access to the data to make any solid conclusions. But from what I've seen, nobody has really treated this Milne model with any seriousness. And that's what I would like to see.